In this video, we're going to cover section 2.2 and learn how to find derivatives of exponential base E functions. So the objective, learn how to differentiate the exponential functions that have base E and then solve applied problems that involve those types of equations. All right, so here's our definition of how to find the derivative of the function e to the x. This is an easy one. The derivative of the function f given by f of x equals e to the x is itself. So in other words, the derivative with respect to x of e to the x is e to the x. All right, so let's find dy dx. So we have that new rule now, but we still have the power rule that we know from before. We have products and quotient rules and chain rules. So we're going to incorporate this new function rule into the others. So we're going to find the derivative of these three functions. Notice here we've got an e to the x in all of them. However, some of them are products, some of them are quotients, so we have to know when to use those rules as well. All right, so for part A, derivative of y with respect to x, this time y is 3e to the x. So here 3 is a constant, so our constant rule says you can factor out the 3, then just take the derivative of the function that involves x. And the derivative of e to the x is itself, so we just simply get this derivative is e to the x times the 3. So we just get the same thing, 3e to the x. Part B, derivative with respect to x of x squared e to the x. This was going to require the product rule because both functions involve x. Here we don't need the product rule because this one is a constant. We can just factor that out. But these both involve x, so we have to use that formula. All right, so the first function, x squared times the derivative of the second. So x squared, the derivative of e to the x is e to the x, plus, then this time it's the second function, e to the x, times the derivative of the first. So the 2x is the derivative of the x squared. So there's a common factor between the two terms. Both terms have an e to the x in them. So we're going to factor that out, e to the x. That leaves x squared plus 2x. You could also have factored out an x. And that would have been fine too. All right, derivative with respect to x of e to the x divided by x cubed. This is a quotient in which both top and bottom involve x, so we have to use the quotient rule. So the quotient rule says you take the bottom function, x cubed, times the derivative of the top, which is e to the x, minus the top function, e to the x, times the derivative of the bottom, which is 3x squared, and then you divide by the bottom squared. So then we're going to clean this up. So again, our common factor here, we've got an e to the x in both terms, and they this time did factor out an x squared because there's at least a second power of x in both terms. So if we factor out x squared e to the x, this factored out, you factored out x squared, so the first term you have an x left, minus, here you factored both the x squared and the e to the x out, so you just have this 3 left. The bottom power of a power would mean multiply your exponent, so that would simplify to x to the 6th. So you would get this x squared then canceling out with 2 of the x's on the bottom, leaving e to the x times x minus 3 on top, and since that canceled out 2 of these, you're left with an x to the 4th on the bottom. All right, so here's 3 more just like the ones we did. So you should probably pause the video and try those on your own. And then when you're finished, you can pick back up and press play and see if you got the answers correct. Part A, dy over dx of 6e to the x, just like that first one, 6 is a constant, it just stays there, and then we differentiate e to the x, which is e to the x, so it's just the same thing. Part B, we utilize the product rule. Derivative of x cubed is 3x squared times e to the x plus, then the x cubed multiplied by the derivative of e to the x is e to the x. You might have had these written in the other order. You might have had this term first plus this term, which is fine. Either way here, you can factor out an x squared and an e to the x, and that would leave, if I factored out x squared e to the x, you're left with a 3 plus, and then an x. They just rearrange that to be x plus 3. All right, this one is quotient rule. So here we take the bottom x squared times the derivative of the top, which is itself e to the x, minus the top e to the x times the derivative of the bottom, which is 2x, and we divide by the bottom squared. So x squared squared is the x to the fourth. Again, you can factor out an e to the x and an x in the numerator. That would leave an x and minus the 2. And if you did that, then the x that you factored out can cancel out one of the x's on the bottom. So that would leave just e to the x times x minus 2 on top, and then x to the third in the denominator. All right, so what if the power of e was not x, but it was some other function? That happens frequently. Usually you don't just have e to the x by itself, okay, but you might have an exponent that involves x. So if I want to differentiate e to some power of x, where x, this power is a function, e to the f of x power, we have to utilize the chain rule. So the way that works here is we would start with the original function, e to that power, because the derivative of e to the x is itself, and then we multiply by the derivative of the exponent. So we have e to the power, the original function, times the derivative of the power. Or if you think of it as u being your exponent, you get e to the u times the derivative of u. So the derivative of e to some power is the product of e to that power and the derivative of the power. All right, so let's do the that rule on these three examples. So y equals e to the 8x. So we take the derivative of that. The rule says write down the original function, e to the 8x, and then multiply by the derivative of the exponent, which would be 8. So you would get 8 e to the 8x. Part B, e to the power negative x squared plus 4x minus 7. Start with the original function, e to that power, and then multiply by the derivative of the exponent, which would be negative 2x to the first plus 4 minus 0, so negative 2x plus 4. All right, this one, e to the power square root of x squared minus 3. So we would start with rewriting that as e to the power of x squared minus 3 to the 1/2. Change the square root to the 1/2 power. Then our rule says you have the original function, e to that power, times the derivative of the power. So this is where our chain rule has to apply. So our chain rule, when I'm taking the derivative of the power, brings down the 1/2, leaves the inside, makes this 1 less, negative 1/2. But as part of the chain rule, then we got to multiply by the derivative of that inside, which is 2x. So cleaning this up, we've got this e to the power x squared minus 3 to the 1/2, and this x here in the numerator. The 2 is gone because it cancels with the 2 on the bottom. So if the 2's cancel, the only thing we're left with on top is this x and this first part right here. The 2's canceled, remember. So then this x squared minus 3 had a negative 1/2, so that thing got moved down to the bottom to make it a positive 1/2, and that's why it's the square root in the denominator. Right, so again, I would pause the video and try to do these 3 problems that are very similar to the last 3 we just did, and then when you're finished, you can press play and see if you got the answers correct. So for part A, f of x equals e to the negative 4x, so f prime is the original function, e to the negative 4x times the derivative of the exponent, which is negative 4, or negative 4e to the negative 4x. For part B, g of x equals e to the x cubed plus 8, so g prime, we start with the original function, e to the x cubed plus 8 times the derivative of the exponent, which is 3x squared plus 8. This one, we would start by writing this as the 1/2. So you would get the original function, e to this power, and then you'd be multiplying by the derivative of the exponent, which would be the 1/2 times the inside to the negative 1/2 times that inside function's derivative is the 2x. So they just put the derivative of the exponent first, then times the original function, instead of the other way around. It doesn't matter because you're multiplying. And then that would clean up the same way. The 2's would cancel. The x, they didn't cancel the 2's, but they should have here. Maybe they do that next. The x stays on top, so does this. This moves to the bottom as a positive 1/2. Yeah, and then they got rid of the 2's a little later. You could get rid of them right here if you wanted to. Okay? So that's how the chain rule applies to an exponential function. And in this case, it's a double chain rule. All right, how about higher order derivatives for exponentials? Find the second derivative of y with respect to x for y equals e to the negative 5x squared. All right, so we're going to first use our chain rule to find our first derivative. So the derivative of this function is the function itself, e to the negative 5x squared, times the derivative of the exponent, which is negative 10x. So we end up getting negative 10x, I just put that in front, times e to the negative 5x squared. So that is the first derivative. Now, if we have to do a second, we're going to take the derivative of this thing. Notice this is now a product. You got something that involves x times another function that involves x. So now we're going to have to use our product rule formula. So this derivative, the first function, negative 10x, by itself, times the derivative of the second, okay, so the second function, e to the negative 5x squared, is e to the negative 5x squared, times the derivative of the exponent, which is this negative 10x. So this is the first function. All of this then is the derivative of the second using that chain rule. Plus, then we have the second function, which is this e to the negative 5x squared, times the derivative of the first being the negative 10x, its derivative is just negative 10. So here you could factor out a 10 e to the negative 5, so both terms, here's your plus sign, both terms have an e to the negative 5x squared, and they both have at least one copy of 10. So they took out 10 times this power of e, so this thing is factored out, and a 10 is factored out. So that is going to leave this, when you multiply these together, you get a positive 10, right? So if you think of that, you get a positive 100. So if you think of that as already being a positive 100, taking out a 10 leaves a positive 10. And you've got an x times an x, so you have the x squared still there, but this got factored out. We took out the 10, and we took out this power, right? So we just have this minus 1 left. You have to have a term, right? So that's just factoring out the common factor there. All right, here's the example. So any of the word problems that are in there just basically are something involving a function that is an applied problem that has an e in it. All right, Franco's Fishing Emporium invested $50,000 in an account that earns 1.25% annual interest, compounded continuously. We talked about the continuous compounding formula in the last section. The value of the account after t years is given by A equals the P e to the power of r t. Okay, so they provide that for you, but we could have figured that out from our last section. They want us to find a of 5 and a prime of 5 and interpret the results. All right, so a of 5 just means plug 5 into the function. So this is the amount you would have after 5 years. 50,000 e to the power 0.0125 times t, plugging in 5 for t, gives me $53,224.72. To find a prime of 5, we first have to find a prime. So you have to find the derivative of your function they gave us. So the derivative of 50,000 e to the power 0.0125t, 50,000 would stay in the front. That's a constant, so you got e to the power 0.0125t times the derivative of the power, which would just be 0.0125. So 0.0125 times 50,000 is 625 times e to the 0.0125t. So then once I find my derivative, then I plug in 5. So if I plug 5 into this function in place of t, we get this. And if I use my calculator to evaluate that, you get 665.31. All right, so the meaning means exactly after exactly 5 years, the value in his account was what we got for part A, $53,224.72. And at that instant, the value is growing at a rate of $665.31 a year. Right? The derivative is the rate of change of the function. So how fast it's increasing. All right, so our section here basically just talks about how to find the derivative of the function e to the x by itself, which is itself, e to the x, and how to find the derivative if you have e to a power, which taking that derivative means it's the original function e to the power times the derivative of the power. Okay, that is the end of section 2.2.